In the previous video, we got into this whole concept of a derivative in trying to understand what it means for, say, a specific physics problem. But the issue is that not every physics problem that we deal with where we want to apply this idea, which is basically the idea of an instantaneous speed. That's actually not a good way to think about it rigorously, but it's a pretty good way to think about it, you know, with at an intuitive level. um, it's really more like the limit of speed around a smaller interval, around shrinking interval. That's the more accurate way to look at it. But either way, the idea is pretty valuable in and of itself because it turns out that all of modern physics or most of modern physics can be described with in this language, which is basically the idea of a derivative. And sometimes because this delta t looks like regular t, sometimes people replace this with h. They might take this away, replace it with h wherever it shows up in this equation. But I actually prefer to leave it in the form of delta t. The only thing I would point out is that delta t is not the same as t. T is sort of our input number that we want to generalize. So if we want to find the velocity at time equals 1, we plug in 1 here, and then the output would be 1. So we get the velocity. We get the velocity at time equals 1 based on the input at time equals 1. Whereas this delta t here, it's really not an input or an output. It's really just sort of a variable. It's really just a limiting variable that we let shrink to represent the smaller interval around the value that we actually care about. So what I want to do in this video is just sort of understand, um, you know, how does the derivative work for polynomials? Derivative work, because a lot of functions in physics can be described with polynomials. So understanding how if you have various distance functions that are represented as, say, a bunch of polynomials, it's really good to be able to understand how that affects them. So that's why I think it's a good place to start. And also just to be a little selfish, it's the easiest. They're the easiest to derive. So we're just going to start off with some basic polynomials. So let's say we have this first equation here, and I'm actually going to make a slight change here. So actually, no, I think I'll keep it. In a normal course, what you'll see y equals some function of x. What I've chosen to do here is actually make x the output, um, and describe the input as t. So in your course, you might wonder, why am I saying y's and x's in my calculus course, but I'm seeing x's and t's here? And the reason for that is that I think it makes more sense to understand how physics actually developed to think about time. Because if you're thinking about time, then you can talk about speed. How fast do things change over time, and actually assign a physical meaning to everything that you're talking about. So I'm going to continue with using basically functions of time. Just keep that in mind if you ever get confused that that the people in your course, they might be talking about y as or x y as a function of x. But anyway, let's say we have our first equation here, and let's just say that it's function t. So x equals t. Actually say x as a function of t equals t. So this is actually one of the simplest. Actually, it's not the simplest. Let's start with an even simpler equation that we could have. So let's just say x equals 0. How about that? So this would be like if you have your ball at a certain height, and then you just never let it go, and you just hold it there forever. And then you try to graph the height of the ball over time, and it's actually just 0. If we're calling this 0 and saying that positive goes in this direction, it's basically just keeping the ball at the same height forever. And we'll say, okay, let's use the definition to determine that. So v of t equals, remember, the limit as delta t approaches 0 of of x of t plus delta t minus x of t all over delta t. And this actually, if we scroll down a little bit, you can, the first step whenever you're trying to basically find a derivative or derive a derivative based on the, or based on the limit definition of a derivative is to basically apply the function. So the function here is 0. So if you plug in a t to here, so basically what you would do is every place in the equation x where there's a t, you would plug in t plus delta t. And then for the opposite here, any place where there's a t, you would basically plug in a t. And that's how you would actually get the expression here. Now, in this case, there's actually no t involved at all. So it's actually just 0. So we got 0 minus 0 over delta t. So now if you think about this, what does this mean? So we clearly have 0 over delta t limit as delta t equals, or as delta t approaches 0. So think about this value. Let's make t very, very small, 0.0000001. What's the output? Well, 0. Make the t even smaller while still not letting it be 0. So, 1 divided by a trillion or 1 divided by a gajillion is still going to be 0. So no matter how small we make this, the velocity is always going to be 0. So in other words, what this is saying is that if we never drop the ball, the speed of the thing is always going to be 0. It's not going to be moving. So that actually makes sense intuitively. So that's basically the simplest function that we could have. Now let's look at basically the second simplest function that we could have. So let's say this time we're not letting the ball drop. We're not holding it, at least. We're letting it drop, and it's covering distance at a linear rate. So where c is some constant. So basically x of t will equal c of t. C is constant. We say, okay, what's the derivative of this? In other words, if this is really how our object moves, and this is actually not really describing, this is not really describing dropping a ball, because like we said, the gravity in that situation, the acceleration due to gravity is constant at a certain rate, but that doesn't necessarily mean that the velocity or that the distance covered is linear. You could think of this as like maybe a car. So like let's say we have a car going here, and let's say the car is basically moving at a constant speed. So that's, I don't want to give away the answer here, but just imagine that, and imagine how much distance it's covering over time. If you wait 1 hour, it covers say 20 miles. Let's say it's going 20 miles per hour. After 1 hour, it covers 20 miles. After 2 hours, it covers 40. After 3 hours, it covers 60. And it just sort of follows this graph. It's basically a linear change, and a linear the distance is a linear function of time, basically, is what we have here. So, let's just plug it in. Start plugging things in. So v of t equals limit as delta t approaches 0. And basically the way that this would work is any point where we see t in this equation, we substitute t plus delta t. So in this spot, we would be, c, and this is actually important because you have to make sure that you it's not enough to do ct plus delta t. You can imagine this as multiplying by t. So you actually have to replace everything inside the parentheses with t plus delta t. That's the trick. You'll get used to these as you do more of them. But basically, if you just plug this in, where c is just multiplied, do this. This is the equation we're trying to solve now. So how would we solve this? Well, let's do some basic distributive properties. So we have ct plus c times delta t minus c of t over delta t. And obviously, ct minus ct, those two cancel out. And after you've canceled those out, you have delta t divided by delta t. So obviously those will cancel out. So the way you can think about this is let's let delta t be 0.000001. It doesn't matter how small or large delta t is. If you multiply c by delta t and then immediately divide delta t, well, it's going to be 1. they're going to cancel out. As one gets super, super small, the other also gets super, super small and ends up basically canceling out its effort. So what we're left with here is actually c. So the v of t in this equation is c. So this is actually kind of interesting. So this is what I was getting at early with the car example. So if you think that if you have what this is saying is if you drive at a constant velocity, your distance equation is going to look like this. It's basically going to look like a line, and this is basically a line with a slope of c, and it turns out that the slope is the velocity. At each point in time, it's going a speed here. We said 20 miles per hour, but this actually makes sense algebraically too, based on the definition of. So let's say let's say this is 3 hours, and we've covered 60 miles. Well, this is actually just the normal definition of this is actually just the normal algebraic definition of of the velocity function. So we do 60 miles divided by 3 hours equals 20 miles per hour, and this is one where you happen to be going at the same velocity at each point in time. So this is basically the second simplest function that we can imagine, and luckily the results still make sense. So remember this. So what we've done so far in this video, we're trying to understand how the derivative definition works for polynomials. So we did the simplest polynomial, a 0th order polynomial. Well, I actually could have done a constant. I chose the constant to be 0. And then we did kind of a first order polynomial, where t appears once. So that's why it's first order. Now let's do a second order and see what happens. So, and by the way, this is the equation that we were working with in previous videos, where basically t x of t equals t squared. So it's second order, and we'll call it times the constant too, just to be consistent. So this is a little bit more complicated. This you can't solve with algebra. This is sort of the whole problem with algebra, why we felt the need to invent calculus in the first place, or at least why Isaac Newton did. Anyway, so let's just apply the definition. So limit of delta t as it is delta, or limit as delta t approaches 0 of, we'll do c times t plus delta t. Remember, anytime where we see t here, we're replacing with t plus delta t in parentheses. So then it'll be squared minus c t squared all over delta t. All right, what now? Well, it looks like we need to FOIL, so we'll just do that. So t squared plus 2t delta t. So you don't get confused. And then, or sorry, that should be c. These should be all multiplied by c. And we get ct squared over delta t. What happens here? Well, ct squared minus ct squared. Okay. And then we have, now we have this whole expression t over delta t. Well, okay, that crosses out. So now you're left with v of t equals c times 2t. So in other words, when your distance function that you covered looks like this, it's no longer the case that you're going at a constant speed. Your speed is now actually a function of time. So your speed is changing at each point in time. So at t equals 1, you'll be going at 2 times c. So you'll be going at this speed, and then at t equals 2, now your speed is actually going to double. The slope of your tangent line is going to double. So that sort of makes sense. It basically, at least intuitively, makes sense that as you go up and up this curve, you're obviously going faster. Your speed is increasing. So your speed is actually increasing linearly, because if we graph this, so if we graph this function down here, we look for here 2c t. So this is just another linear function for the velocity. If this is the distance and this is the velocity, this is just a linear function of t. So if our distance function is a polynomial of t squared, then our speed is going to be a linear function of 2t. So that's sort of interesting to do. And now obviously we did this for a 0th, a first, and a second order polynomial. We could keep doing it forever and ever, but obviously there's an infinite number of numbers we can plug in here before we understand it. So the next thing I want to do is sort of try and generalize this, and this is actually a very smart way to calculate calculate the derivative for some arbitrary polynomial. So let's say we're given some, and it's going to be hard to graph this because it's arbitrary, but I'm going to leave the constant out this time as well. I'm just going to forget about that and just say we're talking about t to the n, where, n is some constant. And basically we want to come up with a rule. We want to come up with a rule that we can use so that if anybody gives us any polynomial of this form, then we can just plug this in, get the right answer. That's sort of what we're trying to do here. So now this is a little tricky if we plug this in. So basically what we're looking at, if we use just the normal definition of the derivative, is limit as delta t approaches 0 of t plus delta t to the nth power minus t to the nth power all over delta t. Now, obviously, if n is any specific number, we know how to deal with that. So if it's 1, then we know how to deal with that. If it's 2, we know how to deal with that. We FOIL. If it's 3, we even know how to deal with that. We basically, just the distributive property on steroids. But we don't know a general way to represent this, unless, of course, you remember the binomial theorem. Now, I'm not going to get into the binomial theorem. It's actually very interesting how it's derived, and it makes a lot of sense, and it kind of puts a lot of different things together after you understand that. But I'm just gonna apply it for now, and I'm just gonna use it without explaining it. So basically, the binomial theorem says that if you have a plus b raised to some power, that is equal to the sum from I equals 0 to that power n of this expression, n over I. That's called it's basically n choose I. It's basically the combination formula. I can get into that later. Of a to the n minus I times b to the I. This is the equation. So for example, if you want to do n squared, so let's say a plus b squared, what does that look like? Well, it looks like if we just follow this. So let's start with I equals 0. What is 2 over 0? This is 2, choose 0. And then a to the power of n minus 0. So a to the n is 2 here, so 2 minus 0. Okay. And then b to the 0, so b to the 0. Plus 2, choose 1. That's 2, choose 1. And then we have a2 minus 1, b1, plus 2, choose 2, a to the 2 minus 2, b 0. So if you actually think of these, what is it? So, and by the way, just using the combination formula, so this n over I is equal to n factorial. And this is actually, I don't expect you to know what or understand what I mean by this, because this is a very unintuitive way to describe it. I'm not really going to get into this yet, but this is the formula, and I can explain it in a lot more depth in another video, but for right now we're just going to take it on faith, sort of. So 2 of 0 would be 2 factorial. And factorial just means if you have 3 factorial, that means 3 times 2 times 1. If you have 4 factorial, that means 4 times 3 times 2 times 1. So it's basically just keep multiplying it by all the numbers until you get to 0. That's essentially what factorial means. So 2 minus 0, so we're talking 2 factorial divided by 0 factorial. And 0 factorial is arbitrarily defined to be 1. They basically do that so that the formulas work. It's a little bit logical, actually, but just keep that in mind. So we're talking 2 factorial, so that would be 2 times 1 over 2 times 1 divided by 1. So this is all clearly going to cancel out to be 1. So this here would be 1 times a squared, b to the 0. Anything to the 0th power is 1. So we're really just looking at a squared for the first term. Now for the second term, we're going to be 2 to the first power. That's going to equal 2 times 1 divided by 1. divide by 1 because n 2 minus 1 is 1, so 1 factorial will be 1, and then 1 factorial is 1 is going to equal 2. So now we're looking at 2 times a to the 2 minus 1 is a plus b to the 1. And hopefully this should start looking familiar. This is the answer that we get after we FOIL it. So for the last one would be 2 to the 2, which equals 2 times 1 divided by 2 times 1, or sorry, divided by 2 minus 2, which will be 0 factorial, and then divided by I is 2 in this case, so that's 2 factorial. So remember, this is 1, so this 0 factorial is 1, and we have 2 over 2 basically. So that actually simplifies to 1 as well, and we get 1 times a to the 2 minus 2, or a to the 0. Anything to the 0th power is 1, and we're left with b2. So basically get b squared. So this is the normal a squared plus 2ab plus b squared that we get when we FOIL. We just found it a different way with the binomial theorem. And the only thing you really need to do is to basically take on faith. Actually, before I get into that, let me just write it out. So remember, we're going to write out this term, but we're going to replace this t plus delta tn with this binomial theorem expansion. So let me go do that. So what are we looking at now? Looking at Vt equals, so the sum for, and we're talking about for x equals t to the n. We're talking about what the answer is going to be there. So we get n over I. I'm sorry, the I starts at 0 times a to the n minus I times b to the I. Or actually, I should replace, sorry about that. I should replace a with t and delta t because that's what we're talking about. So t delta t minus delta t to the n. So, and that's all, actually, this whole thing is going to be over delta t. And obviously we're taking the limit. Delta t goes to 0. So if you think about what we did, all we did was we took this expression here, the t plus delta t raised to the n, and we just used the binomial theorem to rewrite it in this form. And we did a little test run of this form just to kind of give you confidence that it actually works based on something you know. But that's basically all we've done. So I'm going to cross this off. So this is what we're working with now. And the problem is that we need to remember this is really just a series with n plus 1 terms. So that's really what we're looking at here. So we want to find some way to expand the theory or expand the series. And basically there's only two things that you need to take on faith here. So basically n to the 0 equals 1. And if you take n to the 1, actually let me start that first. So let me just list out the first couple terms in the series, and then you'll sort of get an idea of how we can actually come up with a general solution to something that's common. So sorry about that. I just lost my internet connection for a bit there, but we just got it back. So now I'm going to basically pick up where I left off here. So I'm just going to take this series here and list out the first couple terms and basically get an idea of what they look like. So, for here we're going to basically have n to the n 0 combination, and then we're going to have tn minus 0, just setting I equals 0 for the first term in this series. And if you're not familiar with the series notation, this is called sigma notation. It's basically just a way of writing out long series with terms where the terms follow a special pattern. So that's really all we're doing here. And then this tn n minus 0 would be just t to the n, and then this delta I would be to the 0th power, so it would just be 1. So this would be what the first term looks like. And then we have, the second term is going to look like n to the 1, and then it's going to basically be t n minus 1 delta t. And then the next term is going to look like n to the 2 t n minus 2 delta t squared. And then this will just keep going on in this series. And then remember at the end we have minus delta t over 2. So minus delta t, or sorry, not over 2, or to the raised to the nth power, not the second power. So this is basically what we have now. And now if you're smart, you might notice something here. Remember, the idea is we want to basically get rid of as many delta t's as possible and simplify. So if you look at this for a while and you get really smart, remember the problem here is that we have to find some general way to calculate these n choose 0 combination formulas for a general n. Now you really can't do that for n. So let's actually take the first one. So let's actually start trying to do this to try and find some generalizations for these combination formulas. So if we do n to the 0, that's equal to n factorial. And remember, you can't actually list this out because you don't know what n is. N is supposed to be some general number. And then you have n minus 0 factorial, and then 0. Well, actually, you can calculate this without even knowing n, if you think about it. So you have n factorial, n minus 0 is n, divided by n factorial, and we said before that 0 factorial is 1. So it actually doesn't even matter what n is in this case. It's just equal to 1. For any integer n, this combination formula is equal to 1. So that's actually handy. That means this thing is equal to 1. Let's try the next one. So let's try n over 1. Let's try again. So we get, what do we get here? We get n factorial divided by n minus 1 factorial times 1 factorial. Now you might think that you're running into a problem here, but you're actually not, because if you understand the definition of factorial, you can represent this top one as, say this, n minus 1 factorial divided by n minus 1 factorial. And the way you do that, the way you think of, if you're 3 factorial, that's the same as 3 times 2 factorial. That's basically what that is. So like, it's the definition of factorial is you multiply this integer times every integer smaller than it. So obviously this formula is going to hold, and that's what we're doing here. Imagine that n equals 3, so we're talking about 3 times 2 and everything below that. No matter how big n is, this formula is still going to hold. And if you see that, we have basically the same term in the top and bottom, and this just equals n. So that's actually kind of interesting that we can do that. So we figured out the first couple terms. Let's try to find n choose 2 for some general n. Well, that's going to equal n factorial divided by n minus 2 factorial divided by 2 factorial. So that's what we're talking about now. You can actually do the same trick that we did before. So you can do n times n minus 1 times n minus 2 factorial divided by n minus 2 factorial divided by 2 factorial. And this will cancel out. So you'll actually be left with, actually let me write it on the side here. You'll actually be left with n over 2 factorial times n minus 1. And you can do this on and on and on, but obviously we can't, even though we know how to find this in general terms, we can't sit here and just do that for everything. So let's see if we can find a special way with our first terms. So let's actually start plugging in some things and seeing if we can learn anything. So let me get rid of this actually to make room. Yeah, let's just continue here. So talking about, and I'm just going to make a line there. So limit is delta t approaches 0 of, remember this is equal to 1, this is equal to n, and then this is equal to something else. So I'm just going to list out the first few terms. So t to the n plus n times t to the n minus 1 times delta t plus, the rest of these terms minus delta t or sorry, this shouldn't have been delta t. That's a mistake of mine. So this should have been t minus t to the n when I wrote this up here. So forget about this delta. This is just regular t to the n. And I write that all over delta t. Well, do you see anything interesting here? Yeah, we might have a whole bunch of terms here, but this actually cancels out with that. And now the trick here is to notice that we have this delta t on the bottom. So basically what we're going to do, remember, we're supposed to see what happens as delta t approaches 0. So we're supposed to basically get rid of the delta t in the denominator because you can't have division by 0. But if you get rid of that, assuming you can get rid of that, and you can here, then you can basically plug in 0 t equals 0 in the denominator and actually get something that makes sense. So that's actually what we're going to do here and see where that leads us. So it's t delta t approaches 0. We have n times t to the n minus 1. And remember, if this term has delta t in it and we divide that by delta t, obviously they'll cancel out. So we have that. And then we have, I'm just going to write in general terms the rest of the series starting at n equals 2 because, this was the series term for n equals 1. N equals 0. This is n equals 1. And then the rest of this is n equals 2 plus 3 plus 4 plus whatever up to n. Basically, it's going to be n, or divided by I. This is a mistake. That should be I. N equals I times t to the n minus I times t to the, I'll say t to the I minus 1. So to the I minus 1. Now, why am I doing to the I minus 1? If you think about it, well, if we're looking at our equation here, so let's say here, the actual equation is times delta t to the I. But remember, we're dividing by delta t on the denominator. So for example, if you have delta t squared and divide that by delta t, now you only have delta t up top. If you have delta t cubed divided by delta t, now you only have delta t squared up top. So that's why we have this I minus 1 term up here. Now, if we actually start listing these out, so this is the general equation after we divide out delta t from the top and bottom. And you might actually see where we're going here if you're familiar with something in calculus called the power rule. But anyway, as we go here, delta t equals 0. We have n times t to the n minus 1 plus, n to the 2, looking at t n minus 2. And now we're talking this should have been delta t the whole time. And now we're talking delta t to the 2. Remember, I is 2 for the first term, so 2 minus 1, well, that's just going to be delta t to the 1, or delta t, plus, n over 3, t n minus 3. Now we're going to have delta t squared, plus dot, dot, dot. And then in every term, the delta t is going to basically, there's going to be an extra term in there. There's going to be an extra delta t in every term, basically. So, we start off in this term, we're just looking at delta t. Next term, delta t squared. Next term, delta t cubed. Next term, delta t to the 4th, on and on and on, up to n, or up to n minus 2 at least. So, if you think about it, when we plug in, as we let delta t go to 0, those terms actually gonna be 0. So we're actually gonna look at, and remember, we can sub in delta t equals to 0 now that we don't have t in the denominator. The only reason we couldn't do it up here is because you can't have division by 0. If you can find some way to algebraically manipulate this to get rid of that problem, which we did throughout all this complicated reasoning with the binomial theorem, then you can plug it in. Remember, we don't have a denominator anymore. We're just working with the numerator. So you can add 0, and that makes sense. You just can't divide by 0. So anyway, let's plug this in. So n equals t to the n minus 1. There are no delta t terms in here, so nothing to plug in. Plus, n to the 2, t n minus 2 times 0. So we actually don't even care what n equals. We actually don't even care what this term is because it's multiplied by 0 as we let the limit of t goes 0. And same thing here. So, whoops, let me we're gonna have the same situation there. So we're gonna have, some term times 0 squared plus another term times 0 cubed. All these terms, in other words, are going to be 0. So all this is equal to 0, and we're just left with this. And in case you've never seen this before, this is something pretty important, and this is called the power rule. So this is just to finish off. So remember, we were trying to find the velocity, which is equal to the derivative. I'm gonna start using this notation as well. The derivative of x, the rate of change of x, if you want to think of it that way, and this is equal to n times t to the n minus 1 for assuming that x of t equals t to the n. So this is basically the notation for a derivative, at least in single variable calculus. You might either see in your calculus class, if you're talking about functions of x, you might see this, or you might see y prime. Now I'm dealing with x, so I'm dealing with x as a function of t, so I would do dx over dt. This is Leibniz notation. I don't know if you remember Leibniz that I was talking about in a few videos ago. He was the co-discoverer of calculus. He preferred this notation. Newton sort of preferred this notation. So either or, you'll probably see them both in your calculus course. But anyway, this is the answer, and this actually has something important. It's called the power rule for derivatives. We just derived it with the binomial theorem and just the definition of the derivative, and we were able to derive that. So what does this mean in practice? It basically means that let's say what we did is we really solved this for every n, any n that you could do for your polynomial. So if we have a function x of t equals x to the fourth, you say, ooh, x to the fourth, what's the derivative of that? Remember, we want to find the derivative of that. V of t, we want to find the speed at each point in time, or the rate of change, the general derivative rate of change at each point in time. What does this mean? Well, remember, n is 4 in this case. So t to the n, we have, or sorry, I should represent this as t. That's my bad. So we have t to the fourth, t to the n. Well, n is 4, so we follow the power rule, talking 4 times t to the, what's 4 minus 1? 3. So, what about xt equals t squared? What does this imply? Well, it implies that it's 2t. So x prime of t equals 2t. This is actually something we saw before. I don't know if you remember when we were actually plugging in actual numbers at the beginning of this video. This is what popped out. And basically the general idea is whatever n is, whatever this exponent is, drop that in front, make that a coefficient, and then subtract this by 1. And that's the power rule. So now I want to add a little caveat that I did something a little sneaky here that's often not talked about. It's that this is only true, or this is only valid for positive integers. N. So this actual argument that I did doesn't actually prove, like, for example, we wouldn't be able to use this argument to justify x equals t to the, say, 1.5 power. And this actually does have a meaning if you basically look at it as the square root of t times 3 equals t to the 3 halves. It does actually have meaning here, but you wouldn't actually be able to find something like this with a n equals 1.5. The reason for that is that the binomial theorem is only applicable for positive integers. So the binomial theorem actually doesn't make any sense. And in case you're forgetting, that's like, the binomial theorem is the main reasoning we used in order to solve this. We basically replaced this term with what it would be in using the binomial theorem, and we did that to simplify the algebra. But this is only valid for n's that are positive integers. If you have fractional or negative integers here, or fractional numbers or negative integers or negative fractions, then this does not apply. So you actually need a smarter way to apply that, and I just want to give a small taste of that here. There is actually one known proof that proves the power rule for all numbers n, and it's basically using the concept of logarithmic differentiation. And this is a pretty handy. This is pretty handy. You can use it to solve a bunch of different proofs, and if you're given a difficult problem to solve, this is you in a or sorry differentiation logarithmic differentiation. So the idea is take log of both sides, take derivative, or whoops, derivative of both sides, then rearrange. And there are a lot of videos online showing you the basic mechanics of logarithmic differentiation, but I just want to give you a basic idea now. So let's say that we have, and this is not using the limit of a derivative, but this is just another known technique. So yeah, let's say, or let me start off. Let's say that we have the equation x of t equals t to the n. That's the general polynomial of an nth degree. And basically what we do, step one, we take we'll use the natural log. So this is log base e of both sides equals natural log of t to the n. And now we can actually um, we can actually take some we can actually use I should do a step one here 1.5 use log properties to simplify. But basically what you would do here in this specific example is you would use the rule of logarithms that allows you to rewrite this as this. Basically, it basically lets you bring the exponent inside out in front as a coefficient. And I'm not going to go into proving why that is, but that's a known logarithm property. And so now we have this x of t, and then now we're going to differentiate both sides. So we're just going to do that. That's the sign of the derivative. And now this is actually used for a little bit down the road. So I don't expect you to know or sort of even agree with the techniques that I'm about to use, but right now just take it on faith and we can go fill in the details later. I just want to add this into this video so that you see that even though the binomial theorem only applies to integers, the logarithmic differentiation does actually work on everything. So basically what this would be is x prime divided by x of t. So this is the derivative of x um, divided by the function x. That's what I don't want to explain why that is. It's a known derivative for the logarithm combined with the chain rule. If you've never heard the chain rule, and just forget about that. And this one would be basically n divided by t. So we have that, and now we try to step 3 is rearrange. Remember, we're trying to find the derivative of t here. That's not a very good t, but if we basically multiply both sides by x of t, we'll have this. The derivative of t is equal to n times the original function x of t divided by t. And remember, if we remember what t was when we started, what x of t was, it was t to the n for some general n. So if we plug that in here, what are we looking at? We're looking at x prime of t equals n times t to the n divided by t. T to the n divided by t, well, that's equal to t n minus 1 times this n. So this is the power rule too. For x of t equals t n. So power rule through logarithmic differentiation, which is like a known technique. Whoops, sorry about that. differentiation valid for all n. So the power rule is true, even though the first proof that I showed is only valid for various integers. So this is pretty nice. This is actually extremely convenient. If you have any polynomial, what this says is it's actually a pretty easy formula to calculate the derivative, basically define the speed at any point in time. That actually makes things a lot simpler than we would have thought. It's very handy that that happened to be the case. And there are other basic formulas for other kinds of functions that we'll talk about next time. So see you then.